There we go. There we go.
Sorry, it took a minute. I don't know what was
Not a
happening there.
problem. Well,
Yeah.
Pratik, tell me, how's your day going for you?
It's pretty good. I had my first driving lesson today.
How'd that go?
That was fun. I liked it. Yeah.
Good, good. So, how many more do you have to go for to get your license?
So I have that was the first third of my 6 hours. So I have two more of those 2 hour sessions.
Okay,
And then
okay.
after that, I have to drive for after that, it's gonna be till my birthday.
Is that coming up pretty soon?
Oh no, that's in October.
Oh, okay,
So I have to turn 17 before the next step. And then once I turn 17, I can take my driver's test.
okay.
And then once that happens, I can drive on my own.
Hey, that's a big step right there. It's kind of a rite of passage, isn't it?
Yeah, really.
Good, good, good. Now, talk to your dad a little bit about your last exam. He said it didn't go over too well. What's going on?
Well, I mean, I took it and it was the chapter 6 test we were talking about. And I mean, I don't know. I just don't have a good feeling about it. I think he mentioned, I was looking at the group chat, right? I think he mentioned that it wasn't, I don't have the score back yet, but
Hmm.
I mean, there's like these two problems which I don't remember because I don't remember them, but like, I just don't think I did too well on them in
Oh,
general. We'll see what happens. So
was it something that maybe you didn't think you were ready for, or you think you were ready, you just kind of blinked, or
I don't know. Yeah, I think it might have been, it was one of those, again, log base has been one of my, change of base
hmm
with logs has kind of been one of my weaknesses, and we kind of did that. It was a problem where you were adding three fractions and like the base and the denominator and the numerator all had like different bases, and it was like kind of confusing.
okay.
Yeah. So we'll see, and we'll see. I don't
Well,
know. Yeah. But I kind of want to focus on the next thing right now.
yeah, what's going on now in your class?
Well, we took the test on Thursday. I didn't have class on Friday, so and then we had the long weekend, right? Which is I return to school tomorrow, so we haven't touched on anything new yet. But I looked in the calendar, and I think we're doing sequences and series. So how does that work?
Well, sequence and series, that's kind of a big order right there. It's a big topic. Uh, a sequence is basically just a collection of dots. It's a discrete function, whereas a series is the summation of that discrete function.
Okay. Say that one more time.
A sequence, what is that is a discrete function,
Okay. What's a
and a
discrete function?
series is a summation of a sequence.
What's a discrete function?
Functions which are defined for integer values like 1 and 2 and 3, but not 2.1 or 5.4, just for integer values.
Wait, can you give me an example?
Give me 1 second. I'll try to pull something up for us. Okay. Now, there are different ways of how you can denote a sequence. And one of the ways I can denote a sequence is you can say A sub n. What they might do in your class, they might say A parentheses n, or they might use a
Okay.
bracket.
Okay.
Now, this n, it's an index value. It's
Uh-huh.
also like a function value. So if I say f of x equals 1 over x, oftentimes this is
Yeah.
reserved when I see x for what's called a continuous variable. If I say a sub n, 1 over n, this is oftentimes reserved for discrete variables.
I see.
So right here, the f of x is what's called a continuous extension. If you were to look at the function a sub n,
Mm-hmm.
if you were to plot it out, you would have 1, You would have a half, then a third, then a fourth. Okay, that's going to be your a sub n. For the f of x, one over x, you basically essentially connect up those dots.
Oh, I see.
And that's the main difference between these. Now, what they're probably going to get into next is things such as arithmetic, geometric sequences.
Uh-huh.
And there's lots and lots of ways how you can represent a sequence. It's not necessarily going to be unique. One such sequence is something like -1 to the n. This is what's called the alternating sequence. It reverses the polarity between positive and negative.
Mm-hmm.
But I can also use what's called the trigonometric function. And I can model the same behavior.
What's 10?
Well, this right here is pi times n, and this is something you haven't
Oh,
really talked about quite yet. This is what's called the trigonometric function.
okay.
Okay, we'll talk more about that pretty much later after this course, but it's just an example that shows us just more than one way of how you can actually represent a sequence.
Uh-huh.
Now, let me grab a few problems here, and let's take a look at some of them. So for up here, basically, if you want to find out what the term is, you're going to take it and you're going to plug it in. This is what's called explicit form. It's also referred to as closed form because there's no guesswork. I know exactly what the a sub n is. You give me an n value, I can find the a sub n. So if I have a sub n is going to be 2 to the n, I can take it, I can plug it, I can crank it, and I know what it is.
Okay.
Now down here, I guess that's a little bit more implied. This kind of structure is known as a recursive structure in which a sequence is defined by its previous values. That's known as recursion. Now, you're probably going to be working a lot of these. Let's look at the first one here, number 9. So here what I have is a structure. Over here, I have the initial value. It's also sometimes referred to as a seed value or initial condition.
Yeah.
Now, your sequences, they can start off at 1 or 2. It just kind of depends upon what they want you to do. So I can start off at 0. Sometimes they might even start off at 1. It doesn't really matter. So if you're to plug in 1, this is what you're going to get. Then, if you're to plug in 2, this is what you're going to get next. You know what a sub 1 is from the previous one. Take it, drop it, simplify it. Move on to the next one. And then what you see here, if you were to factor it, we're going to have a sub n equals 2 to the n. So this right here is implicit form. I haven't solved for a sub n. Down here is explicit form. I know what a sub n is explicitly. I don't have to read between the lines. Now, this up here, though, is also referred to as a recursion, recursive function, or recursive sequence. Okay, now, does all that make sense to you so far?
I think so.
Okay,
A little bit. I mean, it's kind of still.
yeah, let me grab number 10. And what try number 10? Once you take it out a few terms here, see what a sub 0 was also referred to as a sub naught, and then a sub 1, a sub 2. See if you can figure these out.
So a sub naught equals 1, right?
Yeah. Now I'm gonna make a slight adjustment here. Just make it a little bit easier for you. Okay. Okay, so here write down 1, then move on to the next one.
Right, so 2. So 1 plus 1. So 2?
Right, so you set n equals 0 to get this one. How do you get an a sub 2?
2 plus 1? 3?
Take n, make it 1, and then plug it in. And how do you make an a sub 3?
Set equal to 2.
And plug it in. Okay, we'll check it out a few more terms here. Let's go a4 and a5. Okay, see what you get.
So you set it equal to 3, then you plug it in. So 3 plus 1 equals a sub, oh no. 3 plus 1 a sub 3 equals 4 times 5.
Well, a sub 3 is 12. So you can use this to 12 up here and drop it in.
So 48.
48. Good. All right, make a little more room here for you. Okay, a sub 5 now.
So 4 plus 1 a sub 4 equals 5 times 48, which is equal to 240.
How about a sub 6?
Is that right?
Mm-hmm.
Okay. One thousand four forty, if my math isn't wrong.
Yeah, that's it. So that's how you work these recursive functions. You can say,
Okay.
take them, start plugging them in and cranking out the next one.
Okay.
Now, there is a way to sometimes take the recursive functions, make it into an explicit function, but that's going to require a lot more heavy machinery than really what you're going to be doing in this class.
Okay.
Now, what I want to do is something a little bit more fun. Let's look at these right here. In particular, what I want to do is I want to break the code. I want to crack it open. I want to see what was the function. So let's look at 15. So what I want to do here is I want to ask myself, if I want to figure out what a sub n is, I need to ask myself what's changing and what's not. See, when I go from term to term to term, from this one to this one to this one, I see that the numerator changes the polarity. And the one back here, I can express it as 1 over 1 if I needed to.
Yeah.
Whenever I see this reversal in the polarity, I'm probably talking about something like -1 to the n.
Right.
Now, I gotta make a choice because if n starts off at 0, then 1, then 2, then 3, this would be 1, -1, 1, -1, so on and so forth. If it starts off at 1, and then 2, then 3, then 4, then what you're going to get is -1, 1, -1, 1. So I got to make a choice. And let's see if I make this choice over here. What I would need to do is need to adjust it ever so slightly and look at -1 to the n plus 1. That will then give me my positive, negative, positive, negative. And that's exactly what I see in the numerator. Positive, then negative, positive, then negative. Okay, so that would be my numerator for my a sub n. Then look down below. 1, 3, 5, 7, and then 9. And if this term right here occurs when n equals 1, and this one occurs when n equals 2, n equals 3, n equals 4, n equals 5, here's what I got to do. I got to ask myself, how do I make a 3 from a 2? How do I make a 5 from a 3? And how do I make a 7 from a 4? And then it dawns on me, all these numbers down here, they're all odd numbers. And an odd number is going to be something in the form of 2n and then plus, or even a minus, an odd number. So I can say 2n plus 1, or 2n minus 1, or 2n plus 3, or 2n minus 3. Just got to decide which one I'm going to use. Now, because I made a choice at the beginning where I set n equal to 1, if I plugged in 1 into this equation, I would not get 1. I would get 3, but I need to get 1. So what I want to use is this one instead. Because if I plugged in 1, I'll have 2 times 1 minus 1, which in fact is 1. So there is my closed form. Now, again, you could adjust this lots of different ways. You don't have to start off at 1. I could start it off at 0. And if I would have started off at 0, my sequence would correspond to b sub n. And I wouldn't have to do an adjustment. I'll just keep it as -1 to the n. Because up here again, n starts off at 1. Down here, n starts off at 0. So I do have to know where the n value starts off at. Otherwise, you can't really solve these problems.
Okay.
And then I'll say 2n plus 1. Now, these two answers are equivalent. I can take it, I can adjust it, and I can make them fit one another if I needed to. Let's look at 16. 16, I see in the numerator, positive, negative, positive, negative. And when I see that, I think of the alternating sequence. If I gotta make a choice, I'll start off in at 0. And I also see that I have 1, 3, 5, 7, 9, odd number. And I gotta make sure it lines up perfectly. If I say 2n minus 1, Well, that's positive 1, and I'm getting a negative 1. I don't want that. Rather, what I want is 2n plus 1. And down below, 2. Well, see, I see a 2, a 4, a 6, a 8, and a 10. I can't really decipher what's happening quite yet. I do see that it is an equal difference. And if it's an equal difference, that's what's known as arithmetic. It's all different by a factor of 2. Okay, so sometimes in situations, what you need to do is just go ahead and factor and see if you can crack the code that way. And when we factor it, we see it. See, once again, I'm asking that question, what changes and what doesn't change? What doesn't change is there's a 2 here. So when I look at my formula, there better be a 2 there because I didn't change. But what did was a 1, 2, 3, 4, and 5. And since I'm starting it off at 0, I asked myself how to make a 1 from a 0 and how to make a 1 turn into a 2. And I realize it's n plus 1. Okay, so let me stop there, see if it's all making sense to you.
Um, I think I'm gonna have to go back and watch the video a couple times, but
Not a problem. Let's look at 17, and let you have a try at that one. First thing is, does it change the polarity?
yeah, it does. It goes from positive to negative to positive to negative.
Absolutely. So you got a choice to make here. Do you want n to start off at 0? Or do you want to start off at 1? The choice is yours. You just got to make the choice and go with it. Which one do you want?
To start at 0.
Let's do it. So if we go in this direction, a sub n equals, put it up top. Now, whenever you look at the numerator, here you have 9, 25, 49, 81. Can you crack that code? Factor it.
So 3 times 3, 5 times 5, 7 times 7, 9 times 9.
What changes and what doesn't?
The base changes and the exponent doesn't.
So write it out where the base changes and the exponent doesn't. Crack the code. And then again, you go back one more step. 1 squared is 1. What are these numbers called again?
Perfect squares?
Not perfect squares. They're all odd.
Oh, yeah.
1, 3, 5, and 7.
Yeah,
And
they're
since I'm
all odd.
starting off at 0, the format is 2n plus 1. Okay, take a moment, see if that makes sense to you.
Uh-huh.
Next thing is, what about down below? See, down below, if you write 1 as 1 over 1, you do have 1, 4, 8, 16, 32. Crack the code. How are they changing?
2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times 5.
You
So
have a
the
nice
1, 2, 3,
recursion
4,
there.
5 is changing, but 2 isn't.
Okay, so we're definitely seeing that recursion.
Yeah.
Okay, so if I want to figure something that's a little more closed instead of the recursion, what I can do is possibly factor. Maybe I want to look at it like this. Maybe not. don't quite know what I know until I know what I know. If you know what I know when I say I don't know what I know, you're going to have to
What?
push on it and you're going to have to look at it closer.
Okay.
Now, here, we do see a pattern forming, don't we?
Yeah.
4, 4, 4, 4. That doesn't change. But what does? 1, 2, 3, 4. The 4 terms. Okay, well, maybe I'm seeing something. Maybe not quite yet. So if I don't see it quite yet, keep factoring it. Maybe you'll see it then. And 4 is 2 squared. 8 is 2 cubed. Then that kind of sheds some light back here. It's 4 times 2 to the 0. So it looks like I'm saying 4 times 2. And again, I started off at 0. So my very first term is the 1. The next one is that's what n equals 1. N equals 2. N equals 3. N equals 4. Crack the code. I got a 1. How do I get a 0? I got a 2. How do I get a 1? Got a 3. How do I make a 2? And if I can't crack the code yet, I might want to try factoring again and see if I can recover it. But I see it now. To make a 1 from a 2, take the difference. Now, all this is really only valid whenever n starts off with a value of 1. Because when it starts off at 0, got kind of a problem here, don't we?
Mm-hmm.
So although we did start off at 0, I really just want to take my sequence, start off at 1, and do a little throw case. Since it's not really conforming well when it equals 0, I'm just going to do a slight amendment to it and put it together like that. Okay, now take a moment there to see if that all makes sense.
Uh-huh.
Good. Feeling a little better
Kind
about it?
of, kind of. Not entirely.
It'll take some time to
It's
get
gonna take a
used
little
to.
bit to sink in. I'm just letting it sink in for now, so we can.
Why don't you try number 19? Try to
Okay.
crack that code. Ask yourself what's changing and what's not.
So the 1 is not changing. The does not change.
Good. So just write it out then.
So would that just be n to the first?
Well, not to the first. A sub n equals, and I see a fraction. And what are the fractions? What's happening in the numerator?
They don't change.
You keep it as 1. Oops. There
Am I undoing your work as well?
we go. You are.
I'm sorry. So 1,
Very
right?
good. Now, look down below. It's a little more complicated. Again, ask
It's 1
yourself,
times 3 times 5.
now make a choice. Do you want n to start off at 0 or 1? Choice is yours.
0.
Okay. So what you have to do now is ask yourself, when you look at 1 times 3,
Yeah.
3 times 5,
Yep.
5 times 7.
Uh-huh.
This is the zero term. If that's the first term, if that's the second term, what's the function that you're going to put in right there? And it can't be recursion.
It's basically multiplying only odd numbers together. And it's multiplying like the number before it and the number like the most recent number and the number after that's odd. So it's 1, 3, 3, 5, 5, 7. So the next one will be 7 times 9.
Okay, that's a good observation. What else do you see
Yeah,
about those numbers?
they're only odd. They're above 0.
Good.
No negatives.
That's also a good observation.
Yeah.
So see what you can do then, Pratik, to create 3 from 0 and 15 from 1 and 35 from 2. Crack the code.
How do I create 3 from 0? Um, you add 3 to 0 to make 3, but that doesn't for the rest. Wait, how would you do that? Can you help me a little bit? I can't, I have no idea.
Let's go back.
Okay.
We said they're odd numbers.
Yeah.
And what we say about odd numbers? They're kind of odd.
Yeah.
How many different ways can I write my odd numbers? I'll see if it's down here. Oh, there it is. 2n plus an odd. So if the only thing I have control of is 0, and I know all these are odd, I gotta ask myself, what do I need for right there to make it work?
So 2 times 0 plus 3. 2 times 1. So 2 plus 13. And then 2 times so 4 plus 31. Um,
2n plus what?
plus.
Plus 5? 7? How do you even get that 1? How about plus 1?
How would you get that? I don't understand this. I'm kind of confused today. Sorry.
No, not a problem. If I want to create 1 from a 0,
Yeah,
how do I? The only thing I can control is 0. I gotta do something to it and make 1.
you add 1.
Then I have to look at n equals 1. And I do something to it, I make 3.
Add 2.
Then I do something to it, and I make 5. But what I can't do is I can't come in here and say I want to take the previous term and add 2 to it. That does work, but I need explicit form. I do not want a recursive form.
Okay.
So
So
break
it's
the
going
code.
back to the beginning over and over again.
Yeah. So how do you make a 1 from a 0? How do you make a 3 from a 1? And a 5 from a 2? Why not 2n plus 1? Would that
Yeah,
work?
that works. Yeah.
How are you going to then make a 3, 5, 7? If the only thing you can control is 0, 1, and 2.
So how do you make a 1 from a how do you make a 3 from a 0? How do you make a 5 from a 1? And how do you make a 7? 3n plus 1?
Not 3n plus 1.
Uh, give me a second. 2n plus uh 3.
That's exactly it. You did it.
Okay.
Why don't you try number 20? Crack the code.
So we have the top changing. It stays 1, but it just changes sign. So isn't that, oh my God. Isn't that n to the negative, no, 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 no. -1 to the n.
Mm-hmm. It's called an alternating sequence.
Yeah.
Okay, that's the numerator, so write your fraction bar out. Then start taking the denominator and piecing it together. Pull it apart. 2 and a 4, 4 and a 6, 6 and an 8. If I need to, how about an 8 and a 10? What do you see? And you got to make a choice here, Pratik. You gonna start in off at 1 or 0 or 2 or 3? Where are you gonna start off at?
Does it matter ever?
Not really. They'll tell you in class it matters, but it doesn't really. You just can make a choice and go with it.
So I guess I'll start at 1 this time.
Okay, so if you start off at 1, then this is not correct. You need to have n plus 1.
What?
Well, let me ask you the question. If you looked at -1 to the n,
Yeah,
and if you set n equals 1, you take it and plug it in, is that positive or negative?
that's negative.
But if you
It
said
starts at
-1 to the n plus 1, you take 1, plugged it in, is that positive or negative?
positive.
So what should you do? Use this or use that?
Use that. The second one.
Because it starts off at
Positive.
exactly. So you
I
have
see.
options. You can do -1 to the n, or you can say -1 to the n plus 1. It all depends upon where you start at. Start off at 0, this wouldn't work. But if you started off at 1, it would. And you can even start off at 3, and it still would work. Okay, so
I
this
see.
one over here, n will have to start off at 0. You make a choice. It doesn't matter. It's your choice. It's like when you're driving down the road. Should you turn left? Should you turn right? Doesn't matter. Make a choice and make a turn. Unless the
Okay.
instructor tells you to do it
Yeah.
otherwise.
Yeah.
Okay, so you make a choice and you go with it. And after you've looked at the whole entire numerator, cast your eyes in the denominator and see what's changing.
2, 4, 4, 6, 6, 8, 8, 10. It's the same thing as the other one where it's like, but instead this time it's even, or sorry, odd.
That's right, you have even numbers now.
Yeah, instead of the
How
odd,
do you
but it's the
write an
same
even
idea.
number?
Uh, so it wouldn't be 2n. Would it be just n?
No, it wouldn't just be n because it equals n. If n is 3, is that even or odd? It's
Oh, that's
odd.
odd.
So how do you write even numbers? Just 2n.
Where did it go?
It's down here.
Yep. Um. Oh, was that not what we were doing?
So even is 2n.
Just 2n?
Oh, it most certainly is. Plug in 1 for n, what do you get?
Oh,
2.
I see. Okay, I see it now. Yep, yep, yep.
These are odd numbers.
All right.
So, how are you going to make a 2 from a 1? How are you going to make a 4 from a 1? How are you going to make a 6? Or excuse me, a 4 from a 2 and a 6 from a 3? How are you going to do that?
2n times.
That's right. Now, if you have 4 and 6 and 8,
Yeah.
how are you going to make a 4 from a 1? How are you make a 6 from a 2? How are you going to make an 8 from a 3? You figure that out, you got the problem.
How do you make a 4 from a 1? You give me 1 sec. Is it 2n plus 2?
That's exactly right. Good job.
Thank you.
Or you could factor out the 2, and you could say this.
2 times n plus 1. Okay.
Do the next one down the line. Because 4 is the next even, and 8 is the next even after 6, and so on and so forth.
Mm-hmm.
Good. How you feeling about it?
Better.
You ready for the challenge one?
Kind of. I mean, sure.
18's the challenge one. That's a hard one, but I think you're up for it. Okay, so let me give you a few moments here to think about what you need to do to crack the code. And here's a hint. Do you see a fraction in the first two?
No.
Don't worry about it then. Look at the last three.
Okay.
Okay, let me give you a few minutes to think about it by yourself.
I'm just gonna look around the board for some hints if that's okay.
Yeah, go right ahead.
Um, would you start off with -2 to the something in the top fraction?
Well, you see how it alternates?
Yeah,
Positive, negative idea.
it alternates, right? So,
So you need a -1 to the n or n plus 1. So I wouldn't say -2 like that. I would say -1 to the n or -1 to the n plus 1.
okay.
Okay, so you make a choice. What do you want n to start off at?
1.
Okay, so you want to kind of represent that over here too. We'll say n starts off at 1. Okay, now don't worry about the polarity change, positive, negative. Just look at the numbers. Look at the number in the numerator and the denominator. See what you see.
So the third term, the -8/3, that would be the third term, right?
That's exactly right. So that's also something you want to do. N equals 1, n equals 2, then 3, then 4, then 5. So you got to ask yourself, how do you turn a 3 into a 3? How do you turn a 4 into a 9? How do you turn a 5 into a 27? Crack the code.
Well, I thought we were doing the numerator right now.
Oh, we can do that too if you want.
Yeah, so 3 to the negative 8, right?
You don't want
3
to
to
say negative because
16.
that negative's already been taken care of.
3 to the 8.
That's right. How you turn a 3 into an 8.
Oh, God. Would you add 5? I don't.
Let me give you a moment there to think about it.
Negative 1 to the 2 times n plus 1.
Push on the 8, push on the 16, and the 32. Try factoring it.
3 to the 2 times 3. 4 to the 2 times 4. And then 5 to the 2 cubed, 2 4, 2 fifth.
So Pratik, what changes and what doesn't?
The base doesn't, but the exponent does.
Is it perfectly aligned? Do you have this number and that number being the same always?
Yeah,
Did you just crack the code?
maybe, yeah.
Absolutely. At least for the numerator. Base stays the same. Exponent of n. Okay, so what are you going to do now for the denominator, though?
Well, it's 3, 9, and 27. So it's 3 to the third equals
Well, I don't want to say equals because 3 doesn't equal 27. I have an arrow that says it's getting a map to it.
okay, yeah.
So what stays the same?
The base.
So do you think it might be prudent just to write the base out? Because what it's really changing is not the base, it's the exponent. And
Yeah.
again, we keep asking the same question. What changes and what doesn't?
So it'd be 3 to the n.
Are you sure?
No. Oh, no, no, no. Hold on. 3 to the n minus 2.
That's exactly right.
Okay,
You just cracked the code.
nice.
Now, we did skip over these two at the beginning. Let's just see if it works. Otherwise, I'm going to need a throw case. Plug in 2, plug in 1. What do you get?
Negative 1 to the 2 equals 1 times 4, which is 4. 4 over 0, which equals 4. Yeah.
Does it work?
Yeah, it does. And then for negative 6, it's negative 1 to the negative 6, which is why is that throwing me off? Is that six? Yes, six times two to the first. Oh no, wait, negative one to the one. That's negative one times two to the first, which is two. So it's negative two over three to the negative one.
With negative
So
exponents, you would.
you bring that up. So that's two times three, which is six.
Does it work?
Yeah,
Absolutely.
cool.
You cracked the code. Now it's a hard problem.
Nice.
Okay. You want to try one more?
Sure.
All right. So let me pull one up here. Give me a moment. Okay, let's make it a little more challenging. Crack the code. What changes and what doesn't?
So couldn't we just technically solve it for the first three terms and assume it works for the rest?
Well, not really. It's easy to throw a few throw cases up here where it works for the maybe not for the first five terms, but maybe it works for the last six, or maybe it doesn't work at all for the first three terms or the first 10 terms. That's not really how you should really think about these. In your case, they're not really going to give you anything too challenging in this class. But in the real world setting, no, not at all. You should never look at a few things and make a judgment call based upon three things for all things.
Okay. So
See how
let's
this
say
is a
we're
lot more
starting.
complicated to figure out? You do see the
Yeah,
polarity change, right? Positive, negative. So the
there isn't.
numerators, yeah, positive, negative.
Oh, I don't see that. No, no, I did not see that.
So you do have this feature.
Oh, okay, I didn't see that at all.
And if you start off at 1, that's fine.
Yeah,
Say n plus 1.
okay.
Okay, but what about the denominator? It's more challenging. Why is that more challenging than the other problems?
Because it's not simple. It's
That's
not like
correct.
exponential. I mean, it's not like two to the third, two to the fourth.
So you have them from 19 and 20.
Mm-hmm.
That's more or less easier because what happens to your denominator? Factored.
Yeah, but these don't necessarily
So
do that.
this is telling us something really important about cracking codes. If you multiply them out, you can disrupt the pattern. I could have easily given these problems back here. I could have said, okay, 3, 15, 35, and 63. But that would have destroyed the pattern. You're not going to see
Oh,
it
right.
as easily. So if you keep it in factored form, you might actually discover the pattern and crack the code. So if you can't see it, try factoring it. And do you see it now?
Yeah.
See how it's changing? Now we see the progression of terms. How do I make a 2 from a 1, 4 from a 2, a 6 from a 3, an 8 from a 4? What do I do?
2n.
And then how do I go to 3, the 5, the 7, the 9? Just add one more to it. Good, Pratik, good. All right, Pratik, you feeling pretty good about the sequences, what we talked about here for today?
Yeah.
Okay, okay. All right, we'll have another session I got to run to here, but yeah, keep up the good work. If you need anything else, let me know.
Thank you so much.
All right, as soon as
Sorry
we
for the
figure out what the
rescheduling last
exam's going to
minute.
be, say one more time.
I'm sorry for the reschedule.
Oh, no, not at all. Not a problem.
Yeah.
Uh, yeah, driving exam, that's a big life event right there. That should be celebrated.
Hmm.
So whenever you figure out what you got in the exam, hey, just drop me a quick text so I can, celebrate with you. Hopefully you got that A.
Okay, thank you. Bye.
All right, take care.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.